Today, we're going to look at a very special video editing model called Void. It's not just a simple tool that paints over an object in a video and removes it. What it really tries to solve is a much harder problem. After you remove an object from a video, can the effects that object had on the surrounding environment disappear as well? Let me give you a simple example. If there's a person standing on the ground in a video and you remove that person, a normal video inpainting model can usually fill in the background behind them. But what if that person is interacting with another person? How should those interaction relationships be handled? That is the hardest part of video object removal. The name Void actually stands for Video Object and Interaction Deletion. It emphasizes that this is not just object deletion. The key part is interaction deletion, meaning removing the interaction effects caused by that object. So this is much harder than regular inpainting. In this video, we're not only going to talk about the theory, we're also going to break down the Void workflow inside ComfyUI. And at the end, we'll test it with several real examples to see when it works well and when it falls apart. So without wasting time, let's get straight into it. What you're seeing right now is the Void model open sourced by Netflix on Hugging Face. The official positioning is very clear: remove objects from video, and as much as possible, also remove the interaction effects that object has on the scene. This is very different from how we usually understand video inpainting. Traditional video inpainting mainly asks, how do we fill the hole? But what Void tries to handle is, how do we change the causal relationship? For example, if one object hits another object and we remove the object in front, then in theory, the object behind it should not fall down. Of course, the Void model is not magic. It still depends on how accurate the mask is. It depends on the prompt, and it also depends on how complex the interaction relationship is in the original video. But as a direction, it definitely goes one step further than regular video inpainting. From the official materials, Void is a video inpainting model, fine-tuned based on ComfyUI's Gen Fun, Gen V5 Gen B Gen IMP. It uses a very important concept called a quad mask. This quad mask is not a normal black and white mask. It divides the area into 4 types: the main object region that needs to be removed, the overlapping region, the affected region, and the background region that should be preserved. This is why it can handle interaction effects. Of course, that is one of the complete features of the full model. Inside ComfyUI, the mask we actually use is still only one type. Also, this is a 2-stage workflow. Pass 1 is responsible for generating the basic inpainting result. Pass 2 then uses the result from Pass 1 together with optical flow and warp noise to further enhance temporal stability. You can understand it like this: the first pass removes the object and fills in the image. The second pass tries to reduce flickering and shaking, making the video more temporally consistent. Inside ComfyUI, we use the officially repackaged Void model. It mainly requires several files. The first is the main model. As we mentioned earlier, this is a 2-stage sampling process, so there are 2 main models. The second is the optical flow model. The third is the text encoder. The fourth is the VAE. Because this model is fine-tuned from ComfyUI, the VA we use is also the ComfyUI VAE. In addition, if we want the workflow to generate masks automatically, we also use the SAM 3.1 model. Now let's take a look at the ComfyUI workflow. For easier demonstration, I also built this workflow on Running Hub. In the ComfyUI space, Running Hub is a really great online workflow platform because whenever new models or new extensions come out, it usually follows up very quickly. Running Hub also gives ComfyUI creators an online community platform where you can find a lot of creative inspiration and practical workflows. This workflow is also made up of 5 parts. The first is model loading. The second is reference video processing. The third is mask generation. The fourth is building the inpainting conditions for Void. And the fifth is the 2-stage sampling process, Pass 1 and Pass 2. All right, let's go through them one by one. First, let's look at model loading. Here, we load the T5XXL FP16 text encoder model. We also use the ComfyUI VA as the video VAA. At the same time, we load the optical flow model. Here, we're using RAFTIC large. Then we load the 2 main models. There's also a SAM 3.1 model in the workflow. This is mainly used to generate the mask part. The second part is input video processing. Here we set the frame rate to 24 frames per second, and by default, we extract 121 frames from the video. The output resolution is 672 by 384. Pay attention here. This resolution is not very high because Void's default goal is not ultra-high definition restoration. Its first priority is video object deletion and temporal stability. The third part is creating the mask here. We use the SAM 3.1 detect node. The prompt we use is something like girl with white hair. For this type of prompt, it must be short and very specific. Don't write a long visual description inside the object prompt for SAM 3.1. Its job is not to understand the final image. Its job is to find the object that needs to be removed. The fourth part is the prompt. There is a very important rule here. You can check the official paper for this. In the positive prompt, don't write something like remove somebody. What you should describe is what the result should look like after the object has been removed. For example, if you want to remove a cup from a table, you should simply write something like a clean tabletop. So SAM 3.1 is responsible for deciding who or what gets removed, while the positive prompt is responsible for describing what the scene should look like after removal. The fifth part is the two-pass sampling we talked about. In the first stage, we use the pass 1 model here. The workflow uses random noise plus void sampler and DDM as the sampling process. This gives us a basic result. That result might be pretty good, but it might also have problems. So in that case, we may use the second stage of sampling. In the second stage, the model changes to pass 2. Pay attention here, it does not start again from pure random noise. Instead, it uses void warp noise. This warped noise comes from the optical flow of pass 1. The goal is to help the second stage maintain better temporal continuity. There is also a switch inside the workflow. With this switch, you can skip pass 2. Now let's look at the first example. The input video shows two girls fighting. What I want to remove here is the girl with white hair. In the generated result, the white-haired girl is basically removed. The main subject in the image can also maintain a relatively natural motion state. But pay attention here, the shadow on the ground has not been completely removed. This is a very typical problem. Why does this happen? If the mask does not cover the shadow, or if the model does not correctly understand that the shadow belongs to the affected region of the removed object, it may leave it behind. So when using this model, the mask is extremely important. The quad mask we have here is still relatively simple and direct. Ideally, you should make it more refined. Next, let's look at several other test results. After testing it, my general feeling is that Void's final result is closely related to how complex the interaction is between the subject and other objects. Interaction here does not only mean the character's motion. It also includes whether objects occlude each other, whether they are touching, whether they create physical effects, and whether the surrounding environment is clean enough. The first group is the fighting example I just showed you. The advantage is that the result is still pretty good. The downside is that the shadow is still there. Now let's test another similar example. This one shows a girl skateboarding. This example is really interesting. After we remove the girl, the skateboard is still moving inside the frame, and it can even continue performing the motion. Visually, this result feels very surreal. In real life, if the person disappeared, but the skateboard kept moving like this, it obviously wouldn't match our logical intuition. But from the model task perspective, it accomplished something very important. It removed the person while preserving the continuity of another moving object in the video. For the third group, let's increase the difficulty. The input is a girl holding a glass of overflowing beer, and she is drinking it. This time, I want to remove the beer glass, because the glass may overlap with the hand, the mouth, and the face, and because the glass also affects the character's movement. It is not an isolated object. It has high-frequency interaction with the main subject. From the result, you can see that the overall removal effect is still pretty good. The glass is mostly removed and the video can still play continuously. But you'll notice that near the hands and mouth, unnatural details are more likely to appear. This is completely normal, because the model not only has to fill in what was behind the glass, it also has to reinterpret the girl's motion. Next, let's increase the difficulty again. The input video is a fantasy scene where a snake is wrapped around a girl. Now we remove the girl. This example is very suitable for testing the upper limit of void, because the snake and the girl are no longer simply touching. They are entangled. The boundaries of the subjects occlude each other. The result is still decent. The girl is indeed removed, and the snake and the scene are preserved. But the local details are clearly rough, especially in the areas where the snake and the girl originally overlapped. The model has to imagine the complete shape of the snake again. At this point, it is very easy to get problems like disconnected shapes and unstable local textures. The fifth group is very important. Pay attention to this one. The input video looks fairly simple. A man and a woman are watching a game in the stands, and then the man kisses the woman. Now we remove the woman. If you only look at the motion of the two people, it doesn't seem especially complex. Compared with the fighting example in the first group, this action actually looks simpler. But the problem with this example is not the subjects. The problem is the environment. There are lots of spectators around them. The background is very crowded. Every person may visually overlap with the area being removed. After we remove the woman, the position where she was is indeed filled in. But the content that gets generated looks a bit strange. This shows that the difficulty of video object removal does not only depend on the object being removed. It also depends on whether the background behind it is simple. If the background is a wall, the ground, the sky, or some other relatively simple background, then it is easier to remove the object. But if the background is a crowd of people and everyone is moving, the difficulty becomes much higher. Finally, let's talk about one common pitfall. Void is mainly designed for object removal, but it may not be suitable for removing very small objects. For example, here we have a beautiful woman wearing sunglasses. You want to remove the sunglasses and reveal big eyes. This request sounds very reasonable, but if you use void to do it, it is very easy to get errors. That is because, in this case, the mask region is very small. Void may not be able to achieve the editing effect you want. So for this type of edit, the difficulty is actually not very suitable for void. To wrap things up, void is a very interesting video object removal model. The biggest difference between it and a normal inpainting model is that it does not only fill the hole, it tries to repair the interactive effects caused by removing the object. From a technical structure perspective, it relies on masks, two-stage sampling, optical flow assistance, and temporal stability. From actual testing, void's success rate is mainly affected by three factors. The first is the interaction complexity between the removed object and other subjects. The second is the complexity of the removed area and the background behind it. The third is whether the mask covers the real affected region that needs to be removed. If you want to remove passers-by, isolated objects, or relatively independent elements in the background, and the target area is reasonably large, then you can try the void model. It is not just a simple local editing or patching model. It does have a certain amount of reasoning ability. So what are you waiting for? Go try it yourself, follow me, and become someone who truly understands AI.